Hey programmers, Alvin here. Right now I want to walk through a Python solution for this depth first values problem. And so we'll jump right in over here. We know in this problem what you want to do is write a function that returns a list containing all the values in, of course, a depth first order. We mentioned that we can solve this one using a stack, and we'll start with the iterative version, right? So I'm going to create my stack. I'll just use a Python list. I think that's the most straightforward way to accomplish this. And I'm going to begin that stack with just the root value inside, right? So my stack is going to store instances of node as its elements. Now I can begin my main Python loop, so I can just check while my stack is not empty. So if you're familiar with some Python, you can just check while stack. It is the case that an empty collection type, so like an empty list, would be falsy. A list that contains at least one element would be truthy, so while my stack has some stuff, I'm able to run this while loop. Now when it comes to a single iteration of our algorithm, what I want to do is just remove the top of my stack. So I can do stack.pop. And that removes the last element of an array or a list. It also returns it to me. So I'll call that my current. Nice. And then from there, I can do a few different things with this current. For now, I think I'll just go ahead and print out this current value. So I'm not going to try to put it in a resulting list right now. I'll just kind of debug it as I go. And I know after I consider my current node and its value, I need to look at this node's children, right? So it's left child and right child. So I'm going to go ahead and do, a current.left, and I'm going to push that into my stack. So I'll say stack.push current left, and I'll make it symmetric for current right. However, what I have to be aware of here is it could be the case that maybe this left child does not exist or the right child doesn't exist. If you look at some of the inputs here, if I look at, let's say the C node, let's say that the C node is my current. That means when I do current.left, that value is actually null, right? Or the none value. And so I don't want to put none into my stack. So I'm going to need to guard with an if statement. In other words, I only want to push the left child if I actually have that left child. So I'll check if current.left is not none. Okay, so if it's not none, then I'll push it. And likewise for the right-hand side, if current.right is not none, then I'll also push it. Cool, so this is looking pretty good. I think at this point, that should be our kind of base code for our depth first, at least printing it out. So let's go ahead and just steal some of these manual test cases. Then we can run the automated ones in a little bit. So I'm just going to copy this snippet. We should be able to at least print some of these correct values. Cool, so I'm just writing this tree manually, and I'll bring in the class definition. I'll just run this. If you hit run, this will actually execute the file as is without running any of the automatic test cases. So here I'm getting an error. List has no attribute push because that's a JavaScript thing. So of course here I mean the append, right? So now I'll give that a run once again. And something's going to be off. Here I get ACF BED, which is kind of not what we expect. We mentioned that a depth first traversal would be like ABD ECF. And what you'll notice is we actually technically still have a type of depth first traversal, except we're printing out the right-hand side before the left-hand side. So right now our implementation favors the right-hand side. So it'll travel to the right and then to the left. And if you want to actually adjust that, it's just a matter of the order that you push the children. Based on how I have it implemented right now, it looks like I push the left child followed by the right child. So if I push the left and then the right, that means that the right child is going to end up on the top of the stack for the next iteration. And if the right's on top of the stack, that means I favor the right-hand side first. So if you actually flip the order of these, if you push right then left, then your left-hand side is going to be traveled to first. So I'll just adjust this. I'll run it again. And now I should get the correct print order of ABD ECF. ABD ECF. Awesome. So that's looking pretty good. And now I'm actually ready to probably add in the correct return value. So they mentioned that, hey, you need to return a list containing those values. So let's maybe starting at the top, I'll create that empty list. And as I visit nodes, that is, as I pop them, instead of printing them out, I'll just go ahead and append them to my values. So values.append current val. And then after my while loop, when my while loop is empty or my stack is empty, a while loop will exit, and I can just return the entire values. Nice. So I'll run the test cases for this. We're missing one scenario, but we'll just see it fail. We'll fix it. So it looks like I'm getting none type object has no attribute val on test case 04. So if I look at that fourth test case, right bottom over here, it looks like they call the function and they pass in none, right? They pass in none, basically representing like the empty tree. What happens when I give you an empty tree? Well, what you should do is return an empty list. If we look at our code, we're actually going to put none into our stack, which is already suspicious because we should be putting just instances of node. And so this while loop is going to be true because I have an array or a list containing at least one element. And then when I pop, I'm popping none as my current. And then later on I say none.val, which would throw an error exactly on line 12. And so you're going to have to guard against this like empty tree scenario manually. So I would just check up front, hey, if your root itself is none, then you can just automatically return an empty array. And I think with that, that should satisfy that edge case. So we'll run all these test cases once again. And I believe that will be our nice solution for this depth first values problem. Cool. So here's our nice iterative rendition. Let's also solve this one recursively, right? Because I know if we're using like a pretty explicit stack data structure for our depth first print or depth first values function, then I can also implement this recursively because any recursive code that we write uses the call stack under the hood. And that just happens automatically by your programming language. So if you want to write another version of this, here's how it might look. So I'll start by just stubbing out this function. So we'll say define depth first values, taking in the root of our tree. And like before, I need to kind of guard up top, which really takes the form of a base case. So if I'm going to solve this recursively, I need a base case about the simplest form of our input. Here your input's like a binary tree, right? So what's the smallest tree you could be given? Well, the smallest tree is really the empty tree. So it's not going to be about a tree of just one node. I can think of something smaller than that, right? The tree with 0 nodes. So pretty explicitly here, hey, if my root is none, so if I have an empty tree, then I can just return all of its values, which would be an empty array, right? So just return an empty array. Nice. And that's going to be really nice because it's consistent with the type of our return, right? They ask you for a list back. An empty list is still a list. Cool. And so I know I'm going to have to make recursive calls here because I'm solving this recursively. So that means I call the same function and I have to pass in different subtrees. So I can pass in my left subtree and also my right subtree. And here's how I'm able to like quickly write recursive code. I kind of take the recursive leap of faith, I call it. So when I make this call, I think about what type it returns back to me. It's going to return back a list, right? A list of all the values in that left subtree. So I'll save that to a variable. I'll say maybe my left values. And this call over here gives me all of the values in the right subtree in another list. So I'll call that my right values. So I'll say, oops, just right values. Cool. So I have these two lists. And now I have to think about how I can combine those two lists to find my answer because I am like the root. So imagine that I was stepping through this example. So root would be the A node. And when I make the call to depth first values of root left is the B node. And technically what this result should just magically give back by the power of recursion, it should be a list containing all the values in that subtree, which would just be B, D, E in that order, right? So I'm going to assume I get correct information from this recursive call, right? So I get the values B, D, E. In the same way, if root is A, that means root.right is the C node. And when I make this recursive call, that would give me all the values in the entire right subtree. So that must give me back CF in that order. And now I kind of just have to answer the question, how can I take these two subarrays, combine it with myself because I'm the root, and that would be my entire answer? Well, it looks like I just need to combine these arrays, right? I just take myself A, follow it with all of these elements, and then follow that with all of these elements. So simply put, I can just return in line here. I'll return a new array, and what I'll do is take myself, so root val, and I can unpack or splat all of the elements of my left values array. Also my right values array, so right values. So this is just going to unpack the array, basically just concatenating them all together over here. Awesome. So maybe you're unfamiliar with this like splat syntax in Python. So maybe I'll just demo that. So super quick aside, then I promise I will run the code. So let's say I had some, we'll say people. We have some different people here. We'll say we got Jeff, we got Tommy, we got Rose. And let's say we had, I don't know, new people. And I'll just show you this pattern. So I can create a new array. So whenever I use square brackets, I get a new list in Python, right? And I'll throw down as the first element myself, Alvin, and then I'll spread out or splat all of the elements of the people list. And then afterwards I can put, I don't know, some arbitrary elements. So we'll put in Brian, and we'll also put in Raj, and we'll go ahead and just print out new people. So the syntax I'm trying to reveal to us right now is what happens when we use the splat operator. Imagine we just take the people list and just, took out the square brackets around it, giving us just comma separated things, right? So I'll just run this as a script so you can see how that works. And when I print out new people, I should get Alvin, Jeff, Tommy, Rose, Brian, and Raj. So kind of just took that list and spread it out over here. Nice. So that's all we're doing. And now I think we're ready to run all these test cases. Cool, and there we have our recursive solution for depth first values. So maybe you're not a fan of this splat operator when it comes to like combining arrays. You're gonna see me use that a lot. But what you can also do is maybe just use the classic plus operator to concat. So you can say left values plus right values, like that. But you need to be sure that you put this in a list as well, because you can only concatenate lists. So technically, this has to be its own list first for you to complete this concatenation. So that should actually work as well. It's really up to you. But no matter where you go and implement that line, I recommend you practice both types of solutions. So do know offhand how to code the iterative version of depth first, as well as the recursive version, and do understand why we can write them in both ways, right? Because they both need and utilize a stack, right? In the case of our recursion, we're using the underlying recursive stack, right? The call stack that our programming language just affords us automatically. Cool. And so with that, I'll catch you in the next one where we'll kind of build on top of this knowledge.